Okay, so welcome to CSE 475. The background is 2001 Space Odyssey. And we were just beginning to start. There looks like there are a few student questions that are in the chat. So as I was mentioning a moment ago, I've started grading the exams. I'm a little over halfway through. I should have the exams back by Tuesday. I may have them back faster. It just depends on whether I feel like working this weekend. So that's the true answer to the question. If you really want to know what's going on with the exams and you just can't wait, what I would suggest is that you go onto Moodle and look under the study guide section. I have posted the key to the exam that you took along with the correct answers. So it's the exam and the correct answers. So if you remember how you answered the questions, you should be able to figure out pretty quick where your grade stands. So again, let's see, there are a few questions. Yeah, well, if you have particular questions about your particular exam, we should take care of those, one-on-one during my office hours. There's a question about the programming assignment. The programming assignments are due a week from today. I said on the PDF that it had to run on Eclipse or through the command line. And then I also said that I should be prepared for me to run it on my machine. Is Eclipse required? No. If you give me the source code and you give me an executable file that I can just run from the command line with Java, with a Java command, that would be okay. I normally I will not run the program. Normally what I will do is I will have you run it and I will have you screen share so that I can look at it. But I want the source turned in so that I can play with it. Under very unusual circumstances, for example, I'm looking at your code and it seems to have problems, yet you're showing me a program that's running fine. In that case, I might want to compile it and run it myself to make sure that you're actually showing me the executable of the program, with the same source code. So I have to have the option to be able to run it. But look at the PDF. I ask that you, turn it in. I think it's before 9 a.m. next Thursday. Do you absolutely have to program it in Eclipse? No. But you need to, as long as you're not using 1,000 different files and stuff like this, you should be able to run it pretty much, compile and build it in any environment that you like. On the test question, one of the questions is about partial credit. Most of the questions are either you got it or no, you didn't. The first 20 questions are only 2 points each. Some of the 5-point questions in the second half of the exam, I very occasionally gave partial credit, but that would be something like your equation was right, your numbers were right, and you just made a very simple mistake. So in that case, you might have gotten 2 off rather than 5 off. But generally, most of the time, if you got a wrong answer, it took off all the points. Extra concerned now. Well, again, I shouldn't generalize until I finished grading all of the exams. But guys, the exam was very close to the study guide. that had answers in it. And I've given you all of the lecture notes. I record all the lectures. I put them up on YouTube. I noticed very few people access those lectures. That's fine. I'm putting them up there for you. I can't make you access them. Another thing is when you attend my class in person, I don't allow you to use computers. I don't allow you to use your cell phones. I make you pay attention as best I can. Make you pay attention. Encourage you strongly and don't allow you to do activities that would distract you. But we're doing this online, so, you may have me in the background and you may be, checking your Twitter or your Discord or whatever, and I have no control over that. But I can tell you that if you're not paying attention, if you're not focusing solely on the lectures, you may be able to tell yourself, oh yeah, I got that. And the proof will be on the exams. And again, the exams are very similar to what I give every quarter. The lecture material is very similar. I improve it a little bit each time. I add a little more, take a little bit of old stuff out, but it's 90% what I did last fall, and the exam is probably 90% of what I did last fall, and so the grades should be the same if you guys are putting in the same amount of work. So, I'll be happy to talk to each of you individually during office hours if you want to, and I'm always happy to work with you, but only you can prevent forest fires, and only you can, put in the work. I can't put in the work for you. It's impossible. So anyway, I don't want to get down on people, especially because I haven't finished. I haven't finished grading yet. In the end, the grades may turn out better than I'm afraid they're looking, but I am concerned. Okay, enough negativity about that. Let's get back to the lecture. So the first thing is network tuning, and network tuning can involve a lot of things. One of the things that it can involve is just figuring out parameters like a learning rate or something like that, generating random values for your weights and stuff like that. And other things are called hyperparameters, and those are things like the number of levels you're using, the activation functions you're using, all of those sort of things, sort of the architecture of your network. They can all have an effect on whether or not your neural network is able to learn a particular domain and how well it's able to learn that particular domain. So those are all really, really important things. One thing that I wanted to show is remember how I talked about I showed an Excel spreadsheet, and here it is. And you should be using this, to help yourself work on the programming assignment. I strongly encourage that you use this spreadsheet to be able to verify that your equations are correct before you get, too far off in the weeds trying to figure out what's going on. But this is what I'm showing here, and I've posted this to Moodle. This is the exact spreadsheet that I showed you guys the other day with one little change. And the change is that instead of using initially random variables for weights and biases, I set everything to 0.5. And this is actually what I did right at first when I was creating this the spreadsheet. I'm like, well, the weights and the biases can be random, so 0.5, I'll just set everything to 0.5. That ought to be fine. And when I tried to get this thing to learn, it wasn't learning. And I got real confused. I'm like, oh, well, there's got to be some error in my equations here. And I started tracing things. And I'm like, no, I'm doing that matrix math right. And no, this is the right equation. And yeah, this is, but it wouldn't learn. And I spent a number of hours, tediously going through the spreadsheet looking for errors, going, why the hell isn't this thing learning? And finally, I just said to myself, well, crap, let me actually go online and get a random number generator and just generate random numbers between, -1 and +1 and plug them in. So I just used a random number generator to generate random numbers, and lo and behold, it started learning. But this is a good example to show that, it is important what your initial values are, because like here is, this is the first pass from the first mini batch of Epic 1, and you can see that it thinks both of the outputs should be about close to 1, 0.8 and 0.8. And here's our training set. This guy's supposed to be a 1, this guy's supposed to be a 0, or this guy's supposed to be as small as possible, and this guy's supposed to be as large as possible. Is another way of saying that. Well, what happens with this thing? So this was the first example from the first mini batch in the first epoch, and you can see that it's 0.84, and they're both identical. Well, what happens in the second epoch? Okay, well, look at this. It now thinks both of them are 0.432076, but they're still identical. And then, well, after in the third epoch, they're still identical, 0.459635. And after the fourth epoch, they're still identical. And not only are they still identical, they're not changing very much anymore. Right now it's 0.4749, and then in the next one it's 0.48, right? And then in the next one it's 0.49, and they're both 0.49, and I think that's the last one I computed. But you can see it absolutely is not learning. And these equations are exactly the same equations as in the one that works. The only difference is that in this one, I put all of the weights and biases 0.5. So a neural network is not guaranteed to always, converge on a solution. Could, but it's not guaranteed to. And so one of the things that we frequently do is we will run our neural network over and over again, looking for, the best run and saving the weights from that best run off. So there's a little bit of randomness in there. So I wanted to show that. So the basic idea there is the initial weights and biases matter, and they matter a lot. And that you can get different, because we generally start off with randomly generating weights and biases, you can get different results from different runs of your program. I have a question. How many people have gotten the program running yet? Has anybody gotten the program running yet? Almost. That's good. We got one person who's almost there, a couple of mostlies. A few people are saying they're stuck. Java is hard. Java's not hard. Come on. We are men and women. We can handle it. Okay. I'm glad to see that you guys are working on it. Glad to see that that's happening. Because it takes time to get that program running. Okay, and I see a few people saying they need help, and again, nobody showed up for my office hours this morning, not a single person. So Office hours start at 10 and they go till noon, but, you know, frequently I'm not logged in until about 10:30, but I'm there every morning. So you should take advantage of it. I set that time aside for you. Okay, let's see. So the most important thing about machine learning is data. Data is the key to a successful machine learning effort. If you don't have enough data, and if your data isn't of high enough quality, I don't care what kind of neural network architecture you're using, it's not going to matter. You're not going to get good results. So data is absolutely the key. You got to have, in general, lots and lots of data, and that data has to adequately cover the classifications that you're trying to recognize. So if we were doing the handwritten digits problem, but let's say, you know, we had very few fives in our data set because fives were just an unpopular number, an unpopular digit. Well, then your program would learn not to classify things as fives if those fives didn't show up very often, right? If most of the data, you know, were twos, you know, if you know 2 was a very popular digit, the network would tend to move towards classifying more things as twos. And that makes sense because if you think about probability, right, if your probability distribution between your digits isn't even, the a priori probability that it's a 2 would be higher, right, if you tend to run into 2s a lot more often than 5s. So it's important that you've got a lot of data. It's important that the data cover the cases, and it's really important that you cover, in the real world, that you cover edge cases. So Elon Musk is just releasing the new beta for full self-driving. Although he warns, keep your hands on the wheel, keep your hands on the wheel. Because remember, with the Tesla, your only job is to make sure the car doesn't kill you. As I like to say, but they're just releasing a new build that's a major rewrite of the system, and it can do a lot more things now. It can handle intersections and make left turns and stuff like that most of the time. But to get things to do that, you need lots and lots of training examples of not just what happens most of the time, but training examples to cover odd cases that don't show up very often. And that's critically important if you want the network to recognize those edge cases, you know, and not kill the driver or the passenger, I guess now. In point of fact, getting this data and curating this data, classifying the data, cleaning the data, getting rid of the noise in the data, that is generally these days where the majority of cost and manpower goes in machine learning. So the major cost is not in programmer time to build the network, or even the major cost isn't even paying for all the compute cycles. The major cost is getting the data and labeling the data, because by and large these days still most of the kind of learning that happens in a neural network is learning in which it's called supervised learning. We're going to point out some other kinds of learning, but everything you've learned so far has been called supervised learning, and that requires that humans go through and label all of the data. And that's obviously time consuming to do that, especially because you're talking about lots and lots and lots and lots of data. So right now, that's where most of the effort goes. So what are some things you can do to get better training data? Well, as I said, one get as large a data set as possible. The more data you have, the better. Get rid of noise. Those are corrupted data samples. Sometimes you can do what's called data augmentation, which is to create additional examples. And you have to be real careful in the way you do this. But let's say you got images and you wanted, you had 10,000 images, but you really want 50,000 images. Well, you might be able to do things like rescale the existing images and add the new rescaled images to the database, or add a little bit of noise to the images and add those to your database. And so if you mess around a little bit with your data and add those new things to your data set, the idea is that it'll be more robust because you're learning. It will learn basically to ignore things that aren't important and concentrate on things that are important. So data is the key. And coverage of what you're trying to classify is extremely important. Now, I would like to take a couple of minutes and talk about a social issue that is coming to public awareness. This quarter, I had probably 4 of you, maybe 5 of you, that wrote papers on either racism or sexism in AI. And that's up from last year. There were maybe 1 or 2 last year on that. So this is a topic that clearly is becoming more important in the public conscious. So, we should talk about this a little bit. So you got to make sure that your data doesn't contain biases like ethnic biases, religious biases, racial biases, gender biases, etc. And that's real important, and I can't overstress it, okay? That's important. If you're working on a real-world project that real people are going to use, you have to make sure that the behavior of the machine learning system is fair to everyone. So, for example, there are systems that use facial recognition, and there have been studies that have been done where many times those systems have more misclassifications for black individuals than for white individuals. And, that's obviously bad. You can't have a system, you shouldn't have a system, you should never use a system that produces biased behavior against one group of people, just because of their skin color or just because of their gender or their religion or whatever. So that's problematic. There are even more scary stories, right? The worst that I ever heard was a Facebook. A couple of years ago, Facebook had an algorithm for labeling what appeared in photos. The idea was to find common objects, especially people in photos. And if you found people, well, then you could then try to label that person among your friends and stuff like that, and do that automatically. Well, what they released, and there were actual examples of this. I am not making this up. That the system misclassified some black males as gorillas, believe it or not. So you can't come up with a human behavior, that is more that has any more of a racist behavior than that. Now, was it done on purpose? No, it wasn't done on purpose. How did it happen? Well, again, facial recognition systems tend to be trained on images of people, and if you don't balance, there are more in the U.S. There are more white people than there are black people, or Asians, or other minority groups. That's why they're called minority groups. There are fewer of them. And so you tend to, the data tends to drive towards, that's a white face, so that's a person, and other things not so much. That's horrible. You can't release software like that. So it's critical that your data set be balanced. And when I mean balanced, what I mean is if you're going to use a system, if a system's going to be used by the general public, that includes all genders and all races and all ethnicities, then it better friggin' work fairly for all genders and all races and all ethnicities. Or quite properly, all crap is going to hit the fan, as should happen in a situation like that. So your data is critically important. So I can't stress that enough. It's your data is critically important to a system that doesn't generate behaviors that are inappropriate. One thing, though, I would like to take issue with, most of the papers, not all of them, but most of the papers that were submitted to the class, and really most of the articles that are out there, the general purpose articles that are out there, I think that they mischaracterize machine learning in a sense, and we need to be real careful. Words matter a lot. And it is not proper, in my opinion, to say that machine learning is racist or AI is racist or sexist. To me, when you say that someone is a sexist or a racist, to me that's implying intentionality. There can be unintended racism. I agree with that. There can certainly be racist behavior. And I think when you're looking at a machine learning system, there is no inherent racism in the system. It's an algorithm, and there is no intentionality. It's just making classifications based on patterns in the data. If you feed it data that has unfortunate patterns in that data, then that system is going to develop behaviors that are unfortunate. But we need to be careful. I think it's important that when you talk about it, that we make it clear that machine learning systems can generate behaviors that humans would characterize as racist or sexist or whatever. But the system itself, it's just an algorithm, and there's no intentionality in the algorithm. So I do think that it's important that you talk about behavior. The behavior is wrong. The behavior is inappropriate, and the way you correct that behavior is that you correct your data set. So I think that's important that people think about it in that way. So if you were to ask me, is artificial intelligence racist? I would say no, it's not. Can AI generate racist behaviors? Absolutely. AI systems can generate and have generated behaviors that humans would identify as absolutely racist or absolutely sexist. So again, data is critical, especially if you're working on real world problems. Moving on from that, I wanted to talk about the pros and cons of several of the activation functions that we've talked about and introduce a couple more. We've talked about sigmoid and we've talked about ReLU activation functions, but I really didn't say, well, what do they tend to be used for? What are they good for? What are they bad for, et cetera? What are their shortcomings? And so we're going to revisit those right now, and we're also going to talk about two new activation functions, the hyperbolic tangent and the leaky Rayleigh. So we've got Rayleighs, but we also have leaky Rayleighs. So I think I'm going to share my screen here at this point. And exactly, Jonathan, it's behavior versus intelligence again. This time, when we were talking about sexism, for example, there's no consciousness, there's no awareness, there's no intentionality, right? But that doesn't change the fact that the behavior must be eliminated from the system. Okay, so here's the sigmoid. We've already talked about it. What are they primarily used for? Well, sigmoids are primarily used in feed-forward classification networks. Guess what your MNIST character recognition system is? It's a feed-forward classification network, a fully interconnected feed-forward classification network. And so sigmoids. Now notice it says that I have under primary usage, it says especially in the final output layer. That's new. We didn't just use our sigmoids in the final output layer. We also used sigmoids in the middle layer, and it worked. Why? Well, when we introduced the sigmoid, we said, well, this was one of the very first activation functions that people were able to get good results from, and basically it was chosen because it works similar to how a perceptron works. It's a 0 when your input value is far less than the threshold, and it's a 1 when the value is much bigger than the threshold, normalized here to 0. But the range of the sigmoid is from 0 to 1. That's the range of it, from 0 to 1. And you also notice the way it's drawn here, it makes it a little bit more clear. It's most of the time it's generating either a 0, a value very close to 0, or generating a value very close to 1. And so that gives us two problems. Okay, the first problem is, well, the rate of change, if you're anywhere away from the threshold here, is going to be very slow. The rate of change, it'll be almost 0, and that means that when you calculate a gradient, right, that many times the gradient can be close to 0. The amount of change can be close to 0. And in fact, the example that I showed you guys a few moments ago from my Excel spreadsheet, that was the problem. It's called the problem of vanishing gradients. And so these networks can get into a situation where they don't change very much. In fact, they change almost none, because your value has grown so that the gradients here are so tiny that you only move just a little bit. So that can turn out to be problematic, so that you end up learning very, 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 very slowly, or essentially not at all. Okay, so the problem of vanishing gradients means that you could reach a point where you essentially won't learn anymore. Okay, and that's a problem. So that's one issue with the sigmoid, vanishing gradients. Another issue with the sigmoid is it's not zero-centered. It doesn't have positive and negative outcomes. It only has positive outcomes, right? Down to 0, but it never actually reaches 0. It asymptotically approaches it here. You might say, well, that's fine. And wasn't the perceptron just a 0 or 1? and don't we eventually want to calculate, a yes or a no? And that is true. All of that's true. But that's why you see this, especially in the final output layer, because in the output layer, you don't really need or want negatives, right? You generally want a 1 in one category and a 0 in all the other categories. That's what you want, right? So the sigmoid is good for that. But in intermediate layers, that's not the case. Also noticed in this summary, I reproduced the equation for the derivative of the function there. So I put those so that you'd have them in one place. Okay. So sigmoids are good for feed-forward networks, especially in the final layer. A better function for the hidden layers in feed-forward classification networks, especially in the hidden layers, is the hyperbolic tangent. And this is what the hyperbolic tangent looks like. Essentially, it's a rescaled, shifted sigmoid. So now then the range is from -1 to +1 rather than from 0 to 1. And we've squeezed it a little bit. The equation for the hyperbolic tangent here is 2 over 1 plus e to the -2z, all of that -1. And you can see that you could rewrite it in terms of the sigmoid, right? All you do is you multiply 2 times the sigmoid of 2z. So remember, z was the sum of our weighted inputs plus the bias. You just multiply that by 2, feed it into the sigmoid function, take the result, multiply it by 2, and subtract 1. And that gives you the hyperbolic tangent. If we're going to use it, we need its derivative. The derivative of this is 1 minus a squared, where a is the output of the hyperbolic tangent. So by doing this, everywhere in our first 2 equations where we had a times 1 minus a, we will no longer have that a times 1 minus a, because that was the derivative of the sigmoid function. Instead, we'll have 1 minus a squared in that portion of the equation. So again, why do we have it? We have it because it no longer, it can generate negative and positive values. And in intermediate layers, that can be important. In the final layer, we generally don't want any negatives. So the big advantage is it's zero-centered. Okay, that's the big advantage, is it's zero-centered. It still deals with the vanishing gradient problem. When you get away from the threshold here, or away from 0, it's going to still have, most of the time it'll be near -1 or it'll be near +1. It's only when you're close do things work good. And this is the reason why these vanishing gradients. One thing I showed was that if you start out with weights and biases that are nowhere near random, like I showed on the spreadsheet, you can easily find yourself, in like this region or this region, and the system's usually not going to learn because the gradients are near 0, so it's not going to learn. Another problem that can happen is if your weights and your biases are very different in scale than your inputs. So like, remember I said we want to take our RGB value, our grayscale values of 0 to 255, and we wanted to put that in the range of 0 to 1. You might say, well, Mike, why did you do that? Well, I did that because if you don't, it's not going to learn. Why isn't it going to learn if you don't do that scaling step? Because those values that you're inputting are so big compared to the weights and the thresholds. If you set your weights and thresholds to be between like -1 and 1, that you're going to inevitably be either out here or down here, right? By scaling everything so that the input size and the weight size and the bias size are all in pretty much the same kind of range, what you're doing is you're tending to keep things in this range here where you get good gradients and it can learn. So that's why the scaling is important. So one of the things to check if your system isn't learning after you verified that your equations are correct using the spreadsheet is ask yourself, oh, did I really scale my inputs like Mike told me to? And if you don't, it's not going to learn. Okay, so that's hyperbolic tangent. We looked at ReLU earlier. ReLU is either 0 if you're less than or equal to 0, and it's 1 if it's greater than. No, that's the derivative. The function itself is 0, and then here is just your x value returned as your output, or z value if you're considering that z is the sum of the weighted inputs plus the bias. And so again, there's the derivative. It's either 0 or 1. Why do we have ReLUs? What are their advantages and what are their disadvantages, and where are they used? They're usually used on convolutional neural networks, and we'll talk a little bit about those in a little while. Convolutional neural networks tend to be used for image classification. And you might think, well, weren't our digits or handwritten digits images, Mike? And the answer is yes, they were. And if you used a convolutional neural network, you could get better results. But since the problem of recognizing handwritten digits is so simple, well, it wasn't simple in the 1960s and 70s and 80s when we couldn't solve it, but since it's simple by today's standards, just the fully connected neural network tends to do a pretty good job with it. So that's why you can get 97, 98%. But if you wanted a system that you were really going to release into the wild, right? 98% sounds great, but in reality, that means that of every 100 letters or postcards that you were reading zip codes on, that you would get, a failure 1 in 50 times. And actually, it's quite a bit worse than that because the zip code doesn't have 1 digit, right? Zip codes are what, 7 digits? 5 digits? 5 digits? So, it's 5 times that. So, you're missing what, 1 in 10 or something like that, misreading a digit in a zip code. So while 98% sounds fantastic, and you should be proud of it, for an actual real-world application, that's not nearly big enough, right? Not nearly high enough. ReLUs are normally used in convolutional neural networks for image recognition. And they're also used in deep neural networks too. Convolutional neural networks tend to be a kind of deep neural networks. I guess you could have a convolutional network that wasn't deep, but I've never seen one. So that was the ReLU. Now, what's good about it and what's bad about it? Well, what's good about it is you never have vanishing gradients, right? So even if you have very large inputs, right, or inputs that are positive but close to zero, you'll still have a gradient that will allow you to move. okay? So it's easier to calculate. You don't have the problem of vanishing gradients with a RALU. A problem, though, that you do have is RALUs ignore all negative inputs. Think about that, right? If your Z, right, is less than or equal to 0, your derivative, right, is going to be 0. That means there ain't going to be any change in your gradient, right? Your gradient is going to be 0, so you're not going to move, right? And what can happen is essentially that using these, you can end up ignoring your negative inputs. It's what can happen with the RALU. So they're simple to calculate. They don't suffer from vanishing gradients. They tend to be used a lot in convolutional neural networks and deep neural networks. But you can have this problem where you're ignoring negatives. And as I say in the notes here, that can be a good thing in certain circumstances, that you're focusing on what's important, but it can also be bad in the sense that neurons kind of die off, which can be bad. But all of these things, even neuron, you might say, oh, neurons dying off, that's horrible. But if you look at the biology of how the brain works, actually, when you learn something, what happens is some neurons appear to grow stronger and others grow weaker. They decrease their number of connections. And so part of learning in the biological model seems to be having neurons essentially die. So killing off neurons can be a good thing, not just the result of a wild weekend. Okay. So the advantages of the RALU, the fact that it's easy to compute, the fact that the derivative is easy, the fact that it doesn't suffer from vanishing gradients, it led people to say, well, is there some way that we can kind of not totally ignore things that are negative, inputs that are negative? And that led to the leaky RALU. The leaky RALU, it's also used in convolutional neural networks and deep neural networks. Here's what a leaky RALU looks like. Basically, when you're greater than 0, it's exactly the same. Your slope of this line is still going to be 1. The output is still going to be equal to the input. But down here where you have a negative, right, what happens is that you get you add a tiny positive slope to the line, like 0.01. So the line is not flat here; it's got a little bit of a slope. And so if something plops onto this side, it can still move. Okay, it's not totally ignored; it can still move. Now again, this C is generally very small because you want it very small. It must be much less than 1, right? If it were 1, then you just have a straight line here, right? So don't have a slope of absolutely 0. Have a tiny slope when you're in the negative range, and have your slope of 1 when you're in the positive range. And that will allow you, it's an attempt to solve the problem that RALUs essentially ignore their negative inputs. While retaining the good thing about RALUs, which is that they're easy to compute and that they're that they don't suffer from vanishing gradients. Okay, and so I went ahead and said, okay, well, here are the equations. All right, our 3 equations for backpropagation when you're using leaky RALUs. So if in a regular RALU, it's output minus desired output, times 1. This is the final layer, right, bias gradient. Normally in regular ReLU, this C here would be a 0, which means this whole thing would be a 0, which is why we call it a 0 when we presented ReLUs. But it would actually be C, a very tiny positive number here is what you would have, like 0.01 or 0.001, something like that. And I wrote the times 1 in gray here because you would never actually write that, right? Because it doesn't change anything, but the 1 is actually there. And the same thing when you're doing the bias gradients for the intermediate layers. The first part of the equation is exactly the same, right? It's the weights times the bias gradients. You got to compute the sum of all of those, right? But it's still either times 1 or times C, depending on whether the output is 0 or is greater than 0 or not. Okay. So those were sigmoid, hyperbolic tangent, ReLU, and leaky ReLU. So are there any questions about that? Can different layers use different activation functions? Absolutely, they can. And in fact, I already suggested that that would be a good idea, where you would use hyperbolic tangent in interior layers of your network and use sigmoid in your final layer. Okay. And again, the only difference is in the first two backpropagation equations, you have to remember that the derivative of the output function is in the equation, so it'll change those equations just slightly. Any other questions about that? Okay. That's an interesting way of looking at it, Jonathan, to say that connections dying could be like breaking bad habits. When things are working well, that's a good way of looking at it. But again, depending on your problem and your data and blah, 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 it could turn into a bad thing. If you've got too many neurons nodding off that are ignoring important things, then you've got problems, right? Okay, moving on. In general, more layers and more nodes give better results. If you can afford it computationally, put in more hidden layers and put in more neurons per layer. But what's the downside? Well, it costs a hell of a lot more, right, to do the computations, especially in a fully connected network. It costs more. And so if you can afford more layers and you can afford more neurons per layer, then go for it. It's not going to hurt. It's not going to hurt to overbuild your network, but it's going to cost you more training time, and at some point you're not going to be able to afford more. So, that can be problematic. Got to have a background. Okay. Let's see. Another interesting little thing that I wanted to mention is everything we've done so far, we've used a learning rate that's fixed, okay? Like an ADA, right, of 0.2 or something like that. And we always apply that step size every time we make a step, right? It's always the same little bit that we move, little distance that we move. But what works a lot better is to use a dynamic ADA, a dynamic step size there. And what happens there, if we would adjust our learning rate dynamically. So essentially, as you get closer and closer to your goal, you tend to move a shorter and shorter distance. And why are you doing that? Because if you're always moving at a step size of this, and your goal is now, this far away, well, you're going to overshoot it, and then you're going to bounce back and overshoot it, right? So because at some point your step size is getting in the way of converging on that minima. So if your learning size, how far you move down the gradient, shrinks, then that can be good. And at first, a few years ago, 5 or 6 years ago, people would use, 10 years ago, people would use fixed gradient. And then they went to say, well, I'll just decrease my fixed ADA, a fixed learning rate, not gradient. People would say, I'll just use a fixed learning rate. And then it went to, well, as I get further, maybe each epoch that I work through, I'll make my learning rate a little smaller. So that was the first kind of dynamic approach. And now there are actually approaches that look at the rate of change and adjust the ADA, the learning rate, based on that rate of change, rather than just fixed, change it by this amount every time we go through an epoch. And so that allows you to hone in on the local minima a little bit better. And I see people saying things like, overfitting, and it sounds like a PID controller. I've never played with those. But this is a typical sort of thing when you're trying to do optimization. At first, you tend to want to move pretty quick, right, when you're far away from your minimum that you're aiming for. But as you get closer to it, you don't want to get into that bouncing back and forth overshooting process. So if you make it smaller, you tend not to have that happen. Is overfitting something we should look out for here? Well, yeah, but and no. Getting to that local minimum is really not an overfitting problem. Overfitting happens when your training data is not as representative of the general population as you would like. And so what happens is if you train if your data set's too small or it's not totally representative, the more you train, right, the more you get to where the network has learned to recognize all of those training inputs, okay? If your testing set obviously is not going to be identical to your training set, but if you've overtrained on your testing set and your testing set is not completely representative of your population, what can happen is that it gets too good at recognizing only the things that are in the training set. So when you give it the testing set, it actually does worse because that's not exactly what it's honed in on the training set. So overfitting can be a problem, but generally the way to handle that is I would go back to my little mini lecture 10 minutes ago about making sure you got plenty of data, making sure that data really represents the population that you're concerned with classifying. Those sort of things can control for overfitting. Other questions? Okay. So as you can see, I'm just trying to throw out a lot of ideas here today, and get you familiar with terms that you're going to run into if you try to read about what's going on in neural networks right now. And also to let you know, we've just scratched the surface of machine learning here. There's tons out there, but we've provided a foundation that I think puts you in a really good position to actually read an article about what's going on in neural network research and really understand it, rather than just go, oh, I don't know anything about that. The next thing I wanted to talk about were learning paradigms, okay? And I'm going to talk about 3 of them: supervised learning, unsupervised learning, and reinforcement learning. So these are probably the 3 major learning paradigms that are out there right now: supervised learning, unsupervised learning, and reinforcement learning. Now, what is supervised learning? Supervised learning is exactly what we've spent our time on so far. It's the granddaddy method, the first one that was developed. It's the one where you have training data that's been labeled by humans. And so that's, we're very familiar with that. But that's not the only type of learning. It's the most popular. Most neural networks these days are trained with supervised learning. Okay, you want to teach a computer to be able to recognize traffic signs. You give it tons of images of traffic signs that have been labeled by humans. This is a stop sign. This is a stop sign. This is a stop sign covered with trees. This is a stop sign that's, whatever, on a school bus, right? Because that stop sign doesn't look quite like the stop sign, but it still means stop. And so you have to tons and tons of images labeled by people where you try to get all those edge cases in there so that it doesn't, plow into a school bus that's showing a stop sign because you didn't train it on school bus stop signs. There's no common sense, okay? It's just categorizing the things that we've taught it. So that's supervised learning. So we're pretty comfortable and familiar with that. Another kind of learning is called unsupervised learning. And in unsupervised learning, you're given input data, but it's not pre-labeled by a human, okay? So you're given input data, and you're also given some kind of a cost function. So we're familiar with cost functions, right? They exist in supervised learning, but you don't have labeled data. Instead, the cost function is able to look at the input data and or look at the output and generate some kind of cost. You might say, well, I'm lost. What do you mean? Well, if you think about clustering algorithms, right? A clustering algorithm can give you an indication of how far away things are from one another, with Euclidean distance, say. And so clustering algorithms can give you a cost that you can try to minimize, right? So clustering is one thing that unsupervised learning is used for. Compression and filtering are other applications where, again, you have some measure of cost. You've got input data and some measure of cost. And given that, you don't have to label, you don't have to label all of your inputs, okay? So that's unsupervised learning. One of the third one is probably the second most popular. Supervised learning that we've spent our time talking about is the most popular. Reinforcement learning is probably the next most popular right now. And one of the reasons why it's popular is you use reinforcement learning in gameplay a lot. So in supervised learning and in unsupervised learning, you had input data. In supervised learning, you had not only input data, you had labels that were provided by humans. In unsupervised learning, you didn't have labels provided by humans, but you still had some kind of a function that you could use to compute your error that you wanted to minimize, okay? In reinforcement learning, you don't have data, at least not stacked up in a database somewhere. You don't have data, and you don't know what your cost function is. So you might go, how am I going to do anything if I don't have all my data listed out, and I don't have labels, and I don't even have a cost function? Well, you don't know what the cost function is, but there is a cost function that exists. And essentially what happens in reinforcement learning is you've got some kind of environment that you're going to interact with. And so you give some input to that environment, and that environment generates some sort of response, okay? And that response will have some kind of a cost associated with it, or at least some inputs will have cost associated with it. So if we think of something as simple as Pong, right? Well, if you happen to hit the little, move your paddle up so that the little Pong dot hits your paddle just right and gets past your opponent, well then that's a positive thing. You get a oh, my win number went up, right? But if you don't intersect the little Pong dot like to block it, I hope everybody here's played Pong, right? It's ping pong with little sliding paddles and a pixel for a ball. But if you don't return the serve or whatever, and the ball gets past you, well, then that's a loss. So you can have inputs. You can control the position of the paddle, right? And you can see that, oh, things went really bad here. Oh, things went really good here, right? So you're getting rewards and punishments from the environment, and from that, what the network is trying to do is to generate what's called a policy. Okay, a policy, you can think of it as a way of doing things, that a way of selecting actions to take in this environment that minimizes the cost function. All right. Now again, you don't know what that cost function is, but you can look and you can say, oh, when I did this, when the little dot was going like this, and my paddle was down here and I didn't move it, oh, that's a bad thing. That's giving me loss feedbacks. I'm going to try, and you make random moves, and then finally you find, oh, if I'm here and the little dot hits it, it bounces up. Oh, I didn't get that loss that time. Oh, that was good, right? And so with, tons of playtime, you can see how you can get the feedback you need to be able to learn a policy, right, just from these feedbacks. And you can see that this is perfect for games, because essentially what I'm describing here is a gaming environment. And yeah, I said Pong, but think StarCraft or whatever, right? Any kind of a game where you're getting rewards. So Eric here is asking a question. So reinforcement learning is basing whether it's provided a correct output by whether it receives a positive result based on some heuristic. Well, it doesn't have a heuristic, right? A heuristic is knowledge that a human provides to a game, right, or to a program. So there's no human provided heuristic. It's learning a policy. In a sense, you might think of it, it's not usually expressed this way, but you might think of it as learning its own heuristics. It's learning its own policy. It's learning what actions over time tend to give the most reward and the least losses, right? So when you say heuristic to computer scientists, they're going to think, oh, that's a rule that a human coded, and you don't have that in general in reinforcement learning. But your basic idea there, Eric, is correct. You're on the right track. Are there other questions? Oh, it has to be able to know. You have to be able to tell it this was a win and this was a loss. Okay, so what I said is that when I first introduced this, I said there's no cost function. And then I said, well, there's a cost function. The network doesn't know what that cost function is. Well, the environment has that cost function built into it. So the environment tells you that was a winning move, that was a losing move. You scored a point here, you lost a point here. The environment is giving you that instantaneous feedback, but the network doesn't have some equation to calculate that itself. So the policy that it's learning is attempting to, I guess, infer what that cost function is. That's one way you could think of it, because you've given it inputs, it's telling you good or bad, and sometimes it's telling you, I don't know, you just moved, okay? So that's what's going on there. And one of my Johnsons is talking about Q-learning. I'm not gonna go there. Okay. So those are the types of, those are some of the common types of learning paradigms: supervised learning, unsupervised learning, reinforcement learning. When you hear reinforcement learning, think game playing programs, because that's generally what they're most frequently used for these days. So if you're reading about, you know, OpenAI StarCraft playing program, you're reading about a system that uses reinforcement learning. Okay. But if you're reading about a network that, you know, recognizes stop signs or faces or something like that, you're probably reading about supervised learning. Okay, so one more question here. Does Tesla do that with full self-driving since it's always waiting for drivers to react? Tesla does most of the learning that it has used has been supervised learning. To date, most of the policy, the driving policy, is hard-coded or hand-coded. They're working to reduce the amount of the software that is good old-fashioned AI hand-coded policy and working more towards the network learning policy. There's a company based in Israel. I wished I could remember the name of it, but it's slipping me at the moment. They're the company that is the OEM for GM and really most of the major manufacturers. In fact, Tesla used them. I can't remember the name of it for some reason, but they are very much into this whole question of developing driving policy. Very, very interesting there. Okay, so there are different types of neural networks, okay? And the buzzword that you've all heard are deep neural networks, deep neural networks. Well, what's a deep neural network? A deep neural network is just a neural network. Mobileye, thank you, Haley. So yeah, look up Mobileye. They're a very interesting company. Deep neural networks are just networks that have lots of layers in them. That's all that means. If someone says a deep neural network, they're talking about a network with lots of layers. Now, the problem with a deep neural network is that if you wanted, excuse me, if you wanted to use a deep neural network and you tried to do it just the way that we've done so far, well, you would be building fully connected networks. And as you can see from just our small problems that we've worked on, the number of weights and biases explode. They become huge. And every time you would add a layer, you would be, if it was another fully connected layer, right, you're going to rapidly reach a depth if your layers have any reasonable number of nodes in them, that you're just going to end up with too many weights and biases to change. And so a lot of the deep neural networks tend not to have every layer fully interconnected with every other layer, okay? We've learned the classical, the basic, the foundational neural network architecture, a fully connected feed-forward neural network, okay? Now, everything else grew out of that, but deep neural networks don't tend to be fully interconnected. We'll talk about two networks, convolutional neural networks, often called CNNs, not to be confused with cable news networks, but convolutional neural networks, and another kind of network that's very popular for some applications is a recurrent neural network, or RNNs. So CNNs, convolutional neural networks, and RNNs, recurrent neural networks, are two network architectures that are very popular. Now, and these architectures differ from fully interconnected architectures, the kinds that we've played with. Now, an individual deep neural network could have, normally does have, convolutional layers and fully connected layers. And it can also have other kind of layers, like softmax layers in it. So it's not that, there are a lot of networks that not every layer is identical to every other layer, okay? So convolutional neural networks are normally used for pattern recognition for two-dimensional data. Now let's go, and I wanted to show real quick, this is a short one, a real quick YouTube video here that gives a good 3-minute introduction to what a convolutional neural network is. Let's see here. I need to share screen. Okay.
Let's talk about convolutional networks, or ConvNets. ConvNets are neural networks that share their parameters across space. Imagine you have an image. It can be represented as a flat pancake. It has a width, a height, and because you typically have red, green, and blue channels, it also has a depth. In this instance, depth is 3. That's your input. Now imagine taking a small patch of this image and running a tiny neural network on it with, say, K output. Let's represent those outputs vertically in a tiny column like this. Now let's slide that little neural network across the image without changing the weight. Just slide across and vertically like we're painting it with a brush. On the output, we've drawn another image. It's got a different width, a different height, and more importantly, it's got a different depth. Instead of just R, G, and B, now you have an output that's got many color channels, K of them. This operation is called a convolution. If your patch size were the size of the whole image, it would be no different than a regular layer of a neural network. But because we have this small patch instead, we have many fewer weights, and they are shared across space. A ConvNet is going to basically be a deep network where instead of having stacks of matrix multiply layers, we're going to have stacks of convolutions. The general idea is that they will form a pyramid. At the bottom, you have this big image that's very shallow, just R, G, and B. You're going to apply convolutions that are going to progressively squeeze the spatial dimensions while increasing the depth, which corresponds roughly to the semantic complexity of your representation. At the top, you can put your classifier. You have a representation where all the spatial information has been squeezed out and only parameters that map to content of the image remain. So that's the general idea. If you're going to implement this, there are lots of little details to get right and a fair bit of lingo to get used to. You've met the concept of patch and depth. Patches are sometimes called kernels. Each pancake in your stack is called a feature map. Here you're mapping 3 feature maps to K feature maps. Another term that you need to know is stride. It's the number of pixels that you're shifting each time you move your filter. Stride of 1 makes the output roughly the same size as the input. A stride of 2 means it's about half the size. I say roughly because it depends a bit about what you do at the edge of your image. Either you don't go past the edge, and it's often called valid padding as a shortcut, or you go off the edge and pad with zeros in such a way that the output map size is exactly the same size as the input map. That is often called same padding as a shortcut.
So that gives you, that's a really good, 3-minute introduction to what a convolutional neural network is. I think, Merrick, that video may have answered your question. Eric asked, so if things aren't fully connected on large networks, is that something that's changed dynamically? No. Or are the connections hard-coded? Yes. So the and I think that came through with the little video we just showed. So well, Haley, is it so? It's based on colors? No. Okay. When he is taking 3 colors as the original depth, and he is, wow, my finger vanishes because of my ring. That is weird. When he's taking 3 colors, R, G, and B as the first categories, and he's changing them to K, but what's happening is, let's see if I can.
Patches are sometimes called kernel.
Let's see if I can. No, let me reshare that. It's a good question. I want to go back to that. These start out as meaningless RGB values, okay? But remember he was going into, he said it should be a pyramid, okay? The idea here is that as you get further up the pyramid, these categories should start meaning things like, I detected a curve, I detected a straight line, I detected a shadow. Maybe that's in a level down here. Oh, I detected a nose, I detected an eye, I detected a, so he's talking about semantic representation. So as the dimensionality shrinks, right, but the depth increases, the hope is that these dimensions are starting to map to important semantic features. Okay? So it starts out as just the red color, the green color, and the blue color, but as you move up this thing, you're hoping that the K things you have in here are classes that represent various semantic content that you're interested in, okay? Now, one big advantage of these guys, of convolutional neural networks, is that you can take a convolutional neural network that's been trained, say, to recognize images from the ImageNet set, right, that have, cats and dogs and blah, 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 and people and cars, and retrain that network. Take the network with all of the weights and biases that it's already learned, okay, in these levels, and add a new level or a couple of new levels on the end, okay? And the idea, and it works, it seems to work. That's called transfer learning, okay? So if you want to learn, if you want to teach a thing to say, maybe you taught it on pictures of animals, okay? But you want a network that can distinguish between different kinds of traffic signs. Totally different problem, okay? But you could still use the lower levels of the network that were trained on other kind of vision problems, you would need to train the final layers. But if these intermediate layers have learned to classify things like curves and angles and shadows and those sorts of things, you still need to be able to recognize all of those kinds of things to recognize pictures of traffic signs. So that's one of the huge things that came across from convolutional neural networks is that you could reuse the bottom levels of a trained convolutional network to apply it to a different problem, and you don't have to retrain those lower levels, just your final levels. So that's a real important thing. Yeah, it is very cool. Do we provide the semantic? No. The whole point is it's learning, hopefully, these features on its own. Okay, that's the whole thing that it's doing. It's learning to, hopefully it's learning to identify, like I said, shadows or curves, or, and if you're thinking about a convolutional neural network trained on images of living things, of mammals. So it will learn, oh, that's a nose, even though it's a cat's nose or a dog nose or a human nose are different. That's an eye, okay? These are lips. This is roughly a mouth, okay? And so if it can learn those things, then you can reuse that, what it's learned, to be able to classify other things. You're not telling it, oh, here is a nose, oh, here is an eyeball, oh, here is a head, okay? It is inferring that from the various various inputs itself, okay? Any other questions about that? I think that was a very good question. Okay. All right. We have about 20 minutes left. Let's see. So, in addition to recognizing, in addition to convolutions, you frequently have layers that do things like softmax and max pool. We already talked about softmax. I mentioned it earlier in this lecture, but I mentioned it a lot of lectures ago. When we were first looking at the output of our little neural network, the question was, well, how does it know what the answer is supposed to be, right? I mean, I've got 10 outputs, none of them are 0 and none of them are 1. Now, hopefully, after it's trained, one of them might be like 0.7, and all the rest of them might be less than 0.3. And you go, oh, okay, well, the one that stuck its head up highest, that's the output, right? So that's, in a sense, it is similar, but not exactly the same as softmax. In softmax, you might say, well, I don't just want you to tell me this is definitely a 5 or this is definitely a 3. I want you to give me an indication of how confident you are that it's a 5 or it's a 3. And softmax, what it does is it takes all the outputs of a layer and you add that up to get a total, right? And then you divide each of the outputs by that total. And if you do that, now each of your outputs will represent a percentage chance that it is the thing you're trying to categorize. Because you can treat them as percentages and they all add up to 100%. So again, going back to the situation where I was saying, well, if one of them, is like a 0.7 something and all of the rest of them are less than 0.3, well, if you add up all those numbers and divide everything by that, you're going to get percentages. Well, it's it's 2% chance that it's a 1. It's a 3% chance that it's a 2. It's a 57% chance that it's an 8. Okay, so that's what softmax lets us do, is treat the output of a layer as percentages of confidence in a result. Okay, and that can be really important in intermediate layers. Another thing that's done often is you want to summarize what the output of a layer. And one of the ways that you can summarize the output of a layer is you can use something called max pooling. Basically, when you pool, you say, I got a lot of outputs from this thing, but I want one output. Okay, I want one output. And so it's a way of reducing the scope. And so in max pooling, you find the maximum value of all of the outputs, and you return that as the output of that max pool. So if you're in the example that I was given, the probability of a 5, or the output for a 5 is 0.78, and everything else is lower, well then if you max pool that, you'll just return 0.78. You return one output, and it would be the value of the highest neuron in that pool. So in convolutional neural networks, you tend to have convolutions, softmaxes, max pooling, and then some fully connected levels. And all of these things tend to be combined together into a long chain. So let me see if I can show you that. Okay. This is GoogleNet, okay, and it was one of the networks. I think it is the successor to AlexNet, but it was one of the networks that won the big image recognition prizes. This may have been the first one that did better than a person. And I know you can't read all the little words and stuff like that. That's okay. That's fine. But you can see all of these blue things here are convolutions. All of the red things are pooling layers, and all of the yellow things are soft maxes. The greens are others. Some of those others are probably fully interconnected networks. All right. But you can see that it's a deep network. Here comes our inputs. Here goes our outputs. But it's not like every layer is interconnected fully with every other. You'd never be able to train such a thing. Okay? So in a deep neural network, it's deep, but it's got all of these things that are reducing the dimensionality of the data. I guess you could think of it that way. So that the number of interconnections, while still gargantuan, is not nearly as gargantuan as if you built this thing fully interconnected for 20-something layers here, or whatever that thing is. Does that make sense? Does that make sense? I guess the answer to that's yes, because I'm not getting any questions. So what about these recurrent neural networks that I mentioned? So what are convolutional neural networks used for? Mainly image classification. Recurrent neural networks are generally used for time series data, okay? Things that change over time. So like when you talk to your assistant, right, your Google Assistant, or your Alexa. To understand speech, there has to be some sense of time that passes, because all of the sounds don't happen right at once, and they happen in a sequence, and the sequence matters, okay? So we tend to use things like this, recurrent neural networks, and one particular kind is called the long short-term memory. And so basically what happens is you have an input that goes into a network, right, or a neuron, and it produces an output. But not only does it produce an output, it also produces another separate output that feeds back in as the input for the next input. What are you talking about here? So let's say that, change the sounds. Let's say we've got words. We're trying to do some kind of natural language understanding of a sentence. So the cat, ran, away. So the comes in, right? It produces an output, but it also produces this other thing that feeds in. So when we get to cat, the cat, we're getting feedback from the that came before. And then when we enter the word ran, cat and the influence, the output that comes from ran. And if you unroll this thing, you see what's happening. Here are now the inputs spread out over time, right? And you can see that the output of the first cycle provides input to the second cycle, provides input to the third cycle. So you basically got the concept of time you've captured by having this thing provide a feedback loop to itself. Okay? Now, we're just barely scratching the surface, but what should you get out of this? You should get out of this that, okay, if I want to deal with problems that require me to handle situations that deal with time, that I'm going to need some kind of a feedback mechanism in it, and that's usually done through recurrent neural networks. Now, another thing that's happening right now are transformers. I don't know a lot about transformers. I don't know a lot about BERT and Ernie networks, okay? Yes, transformers are real. Yes, BERT networks are real. Yes, Ernie networks are real. BERT and Ernie are named after Sesame Street. Transformers are named after Transformers. Okay, because computer scientists like to play, right? We're crazy, but transformers are beginning to take over convolutional neural networks, and some people are making brave claims that transformers might replace convolutional neural networks in vision. But that's just a claim that people are making. Why are transformers so popular right now? Well, remember GPT-3 that everybody's talking about? The T is transformer. So there's a lot that's going on there. That's the hot topic right now. And it's only gained traction in the last couple of years, and it's really in the last couple of months, it's pretty much blown up. So the very last thing that I'd like to talk about is, okay, what if you really like this stuff and want to do something with it? Okay. I'm giving you a pretty good theoretical foundation of how basic feed-forward, fully connected, supervised neural networks learn with stochastic gradient descent and backpropagation. And we've looked at a number of the basic popular activation functions, and we've talked about how those activation functions fit into the backpropagation equations. So we've gone through that at a deep level, and I think that puts you in a really good position to start learning about these things if you're interested in it. What I would say is what we haven't concentrated on are tools for learning about neural networks. I want to know that you can do the matrix calculations so that you understand it at a deep level. But if you were going to really play with these things for real, you would not sit down in Java and start writing fully connected neural networks, and you would not be doing the backpropagation equations by hand, right? You just wouldn't be doing that. You would be using tools like TensorFlow. TensorFlow is a network, it's freely available from Google, that interfaces with Python, okay? You should take a look at it. Just all you have to do is Google TensorFlow. And a lot of it it's abstracted to a level that's actually a lot easier to play with neural network architectures using something like TensorFlow. The GoogleNet that I just showed you guys, that's publicly available. That network is out there, free to download and play with. You should be comfortable programming in Python. You should go and look at that program that's in Michael Nelson's book that I gave you guys. I annotated it. I didn't go through it in detail, but I annotated it in my notes, and become comfortable with matrix multiplications through the NumPy, however people pronounce it, network or library, because there you're not actually doing element by element multiplications. You're letting the library handle it, and if you have appropriate hardware, that library can map that hardware, map your equations onto that hardware, and it'll do them in parallel. Okay, so Python, NumPy, TensorFlow, and Keras is another tool that is used quite heavily. I mentioned it in the notes as well. So mostly people use these days TensorFlow and Keras as the tools to actually work in neural networks. So I think it's more important in this class that you get a foundation so you understand networks at the machine learning at the nuts and bolts layer of the actual equations that underlie everything. And I try to give you those, and I try to give you some understanding of why these activation functions, how do these backpropagation equations work, why stochastic gradient descent. You need to know all of those foundations to really be able to understand what the tools are doing at a much higher level. But just like if you want to build a video game these days, you're not doing the linear algebra calculations for ray tracing, right? You're saying here's an object, here's a scene, ray trace it, right? So tools like TensorFlow and Keras let you do those sort of things. But my feeling is that if you come to university to learn the foundation, you go to a trade school to learn, oh, here's the tool and here's how you use this tool, or you learn it on your own. So that's it for the machine learning part of the course. Starting on Tuesday, we're going to start talking about search and state-to-space representation, a good old-fashioned AI, so that we can start getting ready for our game-playing program. Our neural net is due a week from today. I'll be putting up some sort of a sign-up sheet so that we can, electronic or whatever, so that we can have meetings on Thursday and Friday of next week. I should have your exams graded by before class. Are there any questions before we leave? In fact, what I think I'll do is I'm going to go ahead and kill the video or the recording, and if there are any questions, we can wait around after class to answer them. But I hope you guys had fun, and I hope everybody has a much better understanding now of what machine learning actually is. and I'll see you guys on Tuesday. Take care. Bye-bye.